as I said, like this whole thing is nice, but the main problem that we have is we are creating the page table entries just like any other memory works. But page table entries are very important that you want to keep the page table entries as close to your CPU as much possible. Remember that other data that we have in the system, you may be missing them, but in the case of the page table, you will be using them in every access. So as a result, we don't want these our page table entries to be kicked out because we are accessing other data. Still the page table entry may still require a small L1 delay. The solution is to put a separate cache specific for the page table, which we call translation lookaside buffer or TLB. This is a very historic name, but what it means is TLB is a cache for page table. And typically, in order to make this fed, it's a small set associative cache. It's usually not direct map, so in the best case, it can be a fully associative set case in the memory measurement. It maps VPN into PPN. If I had this, data cache maps addresses. You give the address, and then you get the data. In the TLB, instead of address, we give the VPN, which is actually the address, if you wish, okay? Then as the data, you get your PPN. It basically contains the complete page table entries for a small number of pages. So how does it work? To understand this, you have to, again, we go back to our cache structure here. Remember that in the case of a cache, we had three parameters. One was B, which was the block size. In this case, the block size is actually one page table entry. So usually the size of a TLB is specified in the number of entries, PTE actually, not in bytes. It's essentially saying how many lines from the page table does it store. And then the second one was E, which was number of lines per set. And then S was number of sets. So let's say that in this case, the MMU uses the VPN portion of the virtual address to access the TLB. So we are not using the full address. We're just using the VPN. This is the virtual address. And we split this into two, the virtual page offset and the VPN. But we don't use this VPN part in accessing our TLB. And the rest here, then I will be using this to access my TLB. I will have to look at how many sets do I have in my TLB cache. If I have this many sets, here, then I'll be using whatever that number is as my index. So for example, if I have 16 sets here, then I will be using my TLB index is actually 4. Means that I will be using 4 bits of my VPN to tell me which set I should be looking for. And remember that then after that, we set aside the rest of the address as the tag, which is the TLB tag here. So once I pick the particular set, then I have to look at in here. In this case, for example, E, the number of lines per set is actually 2. So I would then check the TLB tag here with the tags here, and also the valid bit. If it's a match, then you get your corresponding page table entry. If it's a miss, then it's a miss. Then you have to go and try to access the table. So the picture now becomes like this. You have your CPU. You send in the virtual address to the MMU. Then we have TLB. TLB is even closer than L1. It's right on the CPU chip. With this one, then you send in the VPN. Then you check whether you have the corresponding page table entry in here. If it's a miss, which we call a TLB miss, then you send in the page table entry address into the cache memory system. And remember, here again, I have my page table. And once I have this, then you put this into your TLB. So note that TLB misses will be rare, and we'll discuss why this is the case.